are both the source and likely cures for what haunts architecture today, such as its mounting contributions to changing climates and its manifold injustices and inequities. It is up to us, to a new generation of architects and faculty, to define, describe, and practice architecture by what they include rather than what they exclude. This is true of well-intended architects interested in timber building. In other words, the first ethical and scientific question of timber architecture in my mind is, what is your operative system boundary and why? What are you including in your description of timber building, and what are you excluding and why? Consider some recurrent claims about the carbon efficacy of mass timber buildings, which in my mind are generally quite specious. The logic in this discourse is as follows. As a tree grows, it locks carbon in one of its constituent components into its cellulistic fibers, and thus locks in the carbon into the tree. While this is ostensibly true from an empirical point of view, there is a systemic error in this logic, that this chemically baked in carbon then goes into the building, and that the building is thus a carbon sink. In this case, what is excluded in this reductive tale of carbon cycling undermines our motivations and methods for considering carbon in the first place. Defining the system boundary of timber buildings as a simple relation between a tree and a building is a systemic error, one replete with its own injustices and ironically full of carbon emissions. Consider this: the vast carbon Canadian forest, which comprises some 40% of the Canadian land surface, is a source of carbon emissions, not a carbon sink. Now, how could a subset of that carbon emissive geography, the tree, suddenly become a carbon sink if its source is the source of carbon emissions? In other words, just because you have an ATM card does not mean that you have any money in your bank account. Canada presently has negative money in its forest carbon account. Anything withdrawn from that carbon account is an ill-fated form of credit, a loan with no methodological hope of repayment. How could a log extracted from a source of carbon emissions through carbon emissive processes, then transported with very carbon emissive methods and processes, then transformed and modified through carbon emissive processes into a CLT panel, then transported again and installed through other carbon emissive processes in construction, how could that element suddenly and magically become a carbon sink? And even if you believe that the kind of brief empiricism that a tree has sequestered carbon, how, by removing that tree and placing a small portion of it in your building, are you not simply exacerbating the carbon emissions of that forest? If this strikes you as odd or worrisome, then please shift your view of timber building. Please right now alter your system boundary and definition of timber building. In reality, a timber building component is not a chunk of sunk carbon from a tree. The carbon in timber does not come from a tree. If we wish to consider the carbon cycle of timber building, we're better served to consider instead broader forest relations and dynamics. One way to do that in carbon terms is to understand a forest as a set of interacting carbon pools. Designers tend to fetishize above ground carbon pools that they reduce through the name of the tree. But this is only one of the carbon pools in a forest, and often not the most significant one. For example, in the Northeast woods where I am, there's as much carbon sequestered in forest soil as there is in above ground carbon pools. In the forest here, in other words, timber building as much a soil project as it is a tree project. It is as much about the dynamics of a forest floor carbon pool as it is about certain trees or wood building components. So if we get serious about the kind of carbon pooling of timber buildings and forests, then we very quickly would arrive at much more regionally specific, that is forest stand specific harvested wood products in architecture. We would not, for instance, blindly advocate for the production and use of CLT panels everywhere in North America. The primarily monospecies stock of the CLT panel is better suited to the forests of Quebec and British Columbia, and perhaps the American Southeast that are characterized by certain dominant species, such as black pine and the boreal forest of Quebec, or southern yellow pine plantations in the southeast. Whereas in other forests, such as the American Northeast, above ground harvested wood products would require a far more nuanced recipe that balance harvesting practices that support carbon cycle dynamics, and concern harvesting that retains and amplifies forest floor carbon pools, all the while harvesting a more broad range of species. This entails a in many cases, much smaller timber building components that are composed of a much more diverse species mix. And if you want to expand the system boundary a little bit further, if you think about this in the Northeast, the small scale, the significant number of small scale landowners compared to Quebec or the Southeast, where there tends to be forests of large scale landowners, you'll end up also with a very different timber building design than these other North American forests. So, never been advocating for CLT factories in the Northeast. It just doesn't make any sense with the forest that you have here. So if we need to cycle or synchronize buildings with forests, this is the kind of thing that we need to get into. So that has something to do about the spatial definition of the system boundary of what we think of as a timber building, but there's also some temporal definitions of the system boundary that are important to consider. So as we want to start to cycle or synchronize buildings and forests, we have to think about the kind of pulsing cycles of these forests. We have to understand that just because we're harvesting one species doesn't mean that that species is going to return. That's very important to what Christian Messier just shared with us, the kind of the complex behavior of forests changing climates. So we need a much more complex adaptive view of our extraction processes of forestry. But we also need a much more complex adaptive view of buildings. So some work that we're doing at McGill is just starting to think about how do we start to set up a model that does synchronize these manifold processes. How can we relate a forest to a building in ways that we have not done before, and starting to model that as complex adaptive systems through ecological modeling. But fundamentally, we just need to understand that forest is a complex adaptive systems. And accordingly, we need to think of timber building and the timber building industry as also as a complex adaptive system. This is one of the difficulties of just setting up these huge CLT plants, is that it may or may not be the right sort of species down the road, 10, 20 years, and we'll have a lot of fixed infrastructure, and that's just a basic problem of capitalism. So much more nimble forms of forestry and timber building processing and production should probably be part of our conversation. So in our minds, I think, or at least in my mind, what we need to work on is a more conjugate understanding of forest building as a kind of single entity. And if we start to think about forest building in the context of carbon pooling, then we would see that I guess we can start to think of buildings, timber buildings, harvested wood products as another type of carbon pool. In this case, by this definition, the 8th carbon pool of forest building. But as soon as we start to think of a building as a carbon pool as part of a forestry practice, then we need to get much more specific. It's not just a kind of fixed number locked into a piece of wood. We have to think about the construction type, the carbon dynamics of CLT versus timber frame versus platform construction are very different. They all have different processing loads, transportation dynamics, relationships with fire, et cetera. So if we're going to treat buildings as an above ground carbon pool, then we need to understand their behavior and their complex behaviors. I've looked at this type, aspects of this in the past by just comparing different types of timber building systems, CLT versus more like low processed timbers versus platform construction, in terms of their mass, in terms of their embodied energy and processing loads, relative to the amount of sequestered carbon in the same type of construction. looking at it in terms of transport, what's actually involved with that versus local versus more continental scale transportation and material geographies. I think there's really significant differences there to consider, both kind of, I'd say technically, but also culturally, that would be involved. So understanding something about those material geographies is a very important part of what I call forest building. And I guess this is a cue up for Ravi's talk, but also looking at that in terms of EMERGY and having a system boundary definition that includes all the biogeophysical inputs that go into forestry and then go into timber building. I still think EMERGY is our best pedagogy for that. We have lots of debates about the numbers and methods, but I still think it's one of the few system boundaries that goes far enough to include the growth of the forest and its understanding of the timber building ecology. So in addition to looking at different forms of wood construction and their specificity as part of that above ground carbon pool, we also need to look at, again, the kind of temporal dimension of this, how timber buildings behave over time. We have to be thinking about their next uses, either of the whole building or of building components, and design for disassembly. We need to be thinking about building envelope durability, because if we want to think about buildings as above ground carbon pools as part of forest building, then we need to make them last a very long time. Otherwise, it's just a kind of very temporary and quite expensive and extravagant way of displacing carbon temporarily. We need to be thinking about, I think, these relatively complex architectural properties of timber building as they're being synchronized with the changing forest that Christian Messier just described. So the task is a formidable one in my mind. We're trying to synchronize two complex adaptive systems that are not historically speaking to each other. So there's a lot of a steep learning curve and a lot of blind spots, but I think those are easy and fun to address. But this is one way to start to think about that forest building concept is treating buildings as above ground carbon pools, harvested wood products. So the path forward in my mind is not a kind of revolution of mass timber in the building industry. I think rather it's a mass evolution of our system boundary definitions of what we think building is, and treating it as a terrestrial process. The answer is not blindly designing, specifying, and extracting massive amounts of timber building as a blanket response. We cannot be content by doing less bad than concrete and steel. This would, in my mind, miss the opportunity and obligations of timber building. We serve ourselves and the carbon cycle of the planet better when we expand the basic system boundary definition of timber and begin to synchronize and maximize the pulsing of carbon pools in the forest, linking cycles of forest growth and building growth. In doing so, we would begin to see the forest for the trees and begin to see the forest through the timber building. In a timber architecture described, defined, and designed through what it includes rather than what it excludes, we will inevitably shift our system boundary to forest building, to a much more a more nuanced appreciation of forest building relations and exchanges. This awareness poses numerous questions for the scope and methods of both our research practices and design practices in architecture. But I think those are all interesting and deeply relevant questions for architecture and for forestry today. So thank you, and I'll put any of my remaining time into the discussion, which I hope will be very interesting. Thank you.
Kyle, can you hear me?
Yeah.
Okay, sounds good. Let me kind of share the screen. Kyle, quick one. Do you see my, which screen do you see? Do you see the presenter screen or the other one?
We see both. We see your present and next.
Oh, okay. So I need to swap it. Okay, this should be good. You okay? Is it okay now?
Very good.
All right. All right. Thank you so much. So good afternoon, everyone, and thanks for joining this interesting talk. And Kyle, thanks so much for kind of introducing the topic of EMERGY. And interestingly, I think most of you may not know that, Kyle and myself, both of us kind of, wrote this amazing book. It's on EMERGY analysis. At some point, when you want to kind of understand more about this, feel free to kind of, pick up the book from your library and then kind of run through some of these things. So my goal here is to kind of, give you an overview of EMERGY analysis, maybe like, for the next few minutes, and then kind of, get into the details of, well, how do we kind of look at timber or wood as kind of an alternative material? Because that's something where exactly we're supposed to kind of move around and so on and so forth. I also want to kind of point out what Kyle just talked about in terms of system boundaries. I mean, that's extremely critical. I mean, the way how you want to kind of set your boundaries in terms of the measurements. And that's something which we have to think about. And I'll kind of, talk about a little bit when we discuss these things. First and foremost, I want to kind of, show this information, which is kind of critical for you to understand where EMERGY analysis kind of sits in the whole suite of tools. We call these as assessing sustainability tools. We have multiple different frameworks, which are much, much larger. We do have evaluation tools, and we also have metrics. If you look at EMERGY analysis, the one which I'm going to talk about for the next few minutes, sits at the reductionist tool, which means there is actually one measurable indicator, which again, I'll talk about this in detail. A very simple example is in all of the other things which we also listened from our previous speakers in terms of carbon dioxide emissions equivalent and so on and so forth, including life cycle assessment. All of these things are also kind of considered as part of the reductionist tool. Basically, as one indicator, you could bring about everything into a carbon dioxide equivalent. So EMERGY sits right there. In terms of metrics are kind of very important for us so that we can evaluate the different types of buildings, the different types of materials that goes into the building. In that case, we have matrices for EMERGY as well. And again, I'll talk about these later on if you're interested. I do have. It's actually one of the publications as part of the building and environment. Okay, so. Okay, let me use my mouse here. Okay, all right. So, all right, okay. So again, in terms of buildings, right, I think this is kind of very critical for us to understand. I mean, in terms of the different phases we're talking about. If you look at buildings, we do have multiple different phases. Majorly, we can think about this as 5 different phases, starting from raw material formation to product stage, construction, use stage, end of life stage. And within all of these stages, we do have multiple small components. A very simple example is, we have these raw materials being kind of, brought into the company in order for us to kind of, for example, CLT, for instance, right? I mean, transportation, the energy kind of used in all those things. What about, bringing or producing the CLT and then kind of transporting to the construction site and so on and so forth. If you look at the different assessment tools, we have life cycle assessment, which is kind of very important, especially in terms of environmental impact, where it kind of captures the impact to the air, water, and land, right? So some of you may know the Athena impact estimator, which is kind of more of a process-based LCE. So if you look at the Athena impact estimator or even the EIO LCA, which is based on the economic input output LCA, it captures from the product stage to the end of life stage, okay? But if you look at EMERGY, what it happens is it kind of captures everything right from the raw material formation stage, and that's huge because we don't kind of consider in typical life cycle assessments, we don't consider the kind of energy that has gone into the formation of all of these materials. So I just want to kind of put it out there so you can understand the kind of the breadth of EMERGY. Again, I just want to this is EMERGY analysis 101 for the next few slides. So I just want to make it real funny also. This is a very simple example, right? So if you look at the food chain and energy pyramids, you have a source, which in this case is the sun. The plants kind of use sun's energy and all of the different ingredients to kind of grow, and then the deer seed is kind of a consumer, and you also have another consumer, which in this case is lime. The reason I want to show this is because I just want to translate this information to the kind of EMERGY and energy, right? So basically what happens is the kind of energy is being concentrated as it kind of moves through this kind of a system, right? I think the next slide would be much more easy for you to understand. what I've done is I've kind of flipped this. This is actually coming from Dr. Dan Campbell. He was one of my PhD committee members when I was doing a PhD at Penn. And then, if you see here, so basically I flipped it. And what you see here is kind of a very interesting kind of a description of emergent analysis. Basically what happens is from left to right, as the kind of energy is being kind of consumed, it's much more, it has a little bit more work. At the same time, there is one other interesting unit which I want to bring about, which is called the transformity. So transformity is actually the energy, all of the different types of energy that's being kind of consumed to kind of have one amount of joules, which you could actually is kind of equal to work, right? So basically, you go from left to right, your transformity kind of increases. And if you look at emergent analysis, we assume that the suns, which kind of is used by almost 98% of all of the different living and non-living organisms, things, right, on the Earth. So it's actually 1.0 solar M-joule. So that kind of gives you information about what emergent analysis is. I want to kind of transfer this information to a building, and then you'll understand where we are going, right? So this is a very nice illustration of a building. So basically, buildings do have boundaries. If you look at this particular building, we have windows, we have walls, and so on and so forth. So basically, we do have kind of an envelope as a boundary. And then we do have external forces such as the wind, the rain, the sun, so on and so forth. That kind of it kind of creates an environment which the building is supposed to kind of operate given all of the different weather conditions. So if you look at building as kind of a storage system of energy, right? So how do you kind of look at all of the individual components? So that's the whole idea of energy calculation, right? So I'm going to transfer this to a next slide where you will see how we create an energy diagram from this slide to this one. So this is kind of a very simple representation of the different building systems. Okay, and this again is coming from the book which Kiel and I kind of work together. Again, the way how it's represented is kind of we wanted to capture all of the renewable inputs that has gone into the site as well as to the material manufacturing and everything. In addition to this, we also wanted to kind of understand all of the other inputs. For example, natural gas. What about electricity? The different materials, the labor that's gone into this. When we talk about labor, it is not just physical labor. What are the services that's being provided by the architects, the engineers, and so on and so forth, right? So everything can be captured, and then we could kind of use that to kind of analyze and evaluate one weighting over another. So this is kind of interesting. The reason is once you understand all of the different materials and the services and all of the energy that has gone into a building, you could kind of make some changes to some of these different materials and then say, hey, you know what? How does this new building look like in terms of, looking in terms of, energy systems, right? So that's one other thing. You could actually have this as a very simple system like what we show here, or you could also kind of go in depth in terms of looking at every individual system. For example, the solar hot water system by itself has a storage system. And then in addition to that, there is so much amount of materials that has gone to the development of that solar hot water system and so on and so forth, right? So, but again, you can understand, you could literally go in depth of everything in terms of emerging. One other thing which I want to talk about here is something which we have to understand, because it is not just kind of running an emergent analysis and saying, hey, you know what, I got this number, right? The number doesn't mean anything at this point in time. That's one of the reasons why we have metrics, and in this case, we do have evaluation indices. These are evaluation indices that will tell you how to kind of optimize a building in terms of changing some of the building materials. Why do we need to use concrete? Can we replace that with timber? Or what about the walls? And what about different kind of systems, flooring systems, and so on and so forth. So what you see here is a typical emerging systems diagram, right? On the left, we have sun, rain, wind. We call them as renewable energy systems, and then we have local non-renewable resources. For example, when you have a site boundary, all of the sun's rays radiation that falls onto the site boundary is actually called the local non-renewable resources. That includes the rainwater, that includes all of the different forces, geochemicals, and so on and so forth within that site. In addition to that, it's very difficult for us to kind of develop a structure without purchasing from the outside, and those are called purchased inputs. And there are two different categories within that. One is called the purchased renewable input. Another one is called the purchased non-renewable input. Okay, a good example is timber is actually a purchased renewable input. Okay, so if you look at the process from left to right, as the structure kind of is being kind of used to build, it kind of nothing but a storage system, and then over a period of time, there's a lot of depreciation, this kind of disposal, everything kind of happens, especially at the end of use of the actual lifetime of the building, right? So we have 4 of these different things which you want to understand. One is the R, which is the renewable systems. The N is the non-renewable resources. We have FR and FN, which is total purchase inputs. And then if we total everything up, it actually becomes the yield. Yield is the total amount of emerging, right? But there again, this is not an index, this is the total number. But then if you go to the next slide, this is actually an index. There are 5 indices which kind of helps us to understand how we can tweak the different composition of the building or the specification of building materials. Okay, a very simple thing here is called the percentage renewability. So, so basically, if you look at the equation, I think it's kind of straightforward. So it shows the percentage renewability is actually R plus FR divided by Y. FR is actually the renewable purchase input. So basically, think about this. If you're completely replacing all of the floor from a certain system to wood or timber, so basically what happens is your FR actually increases, which means you have a higher percentage renewability. The good thing is, one could actually do these alternators one by one and then kind of even potentially optimize some of the materials based on the information that's available. Okay. Similarly, there's another index. It's called the EMERGY. It's called the EMERGY investment ratio. In this case, it has to be lower, and then we have another one which is called EMERGY yield ratio, and so on and so forth. I don't want to spend too much time here, but I just want to give you a flavor of how we could kind of literally optimize all of the building materials using EMERGY as a concept. There are 2 other indices. One is the environmental loading ratio, or ELR, and the last one, which is kind of the measure of overall sustainability of a system, which is called the EMERGY sustainability index, and the objective here is actually ESI. What we have done, myself and Kiel, in this particular book, is we have literally given you examples in terms of how do you kind of look at all of these different alternatives and try to kind of optimize a building if you're running this with EMERGY, right? And again, I just want to show you a simple table. And if you look at the way how it's calculated, so we do have the different inputs. Again, these are kind of categorized based on the renewable inputs. We have the non-renewable storages, and then we have to have the purchase inputs. Within the purchase inputs, there are 2 different categories, as you may know now, renewable and non-renewable. The one which I highlighted, which is the item number 12 right here, is actually the construction materials. And I want you to pay attention to the total number. It's actually 4.53 exponential plus 18. That's the largest number right here, one of the largest numbers, right? I mean, we do have another one, which is chill water, that's sort of electricity and so on and so forth, for the entire lifetime of the building, which is 75 years. If you remove the operational energy use, pretty much construction materials is actually the largest number. And that's exactly where we as architects and engineers can kind of, make changes to that, right? So that's the whole idea. Okay, so the next part of the discussion is going to be about, how do we look at wood or timber as an alternative? This is kind of very critical. On the right side, I've kind of showed you an energy systems diagram. It's kind of very similar to what I showed you earlier. This is kind of, talks about the boundary, and then we have the envelope as a structure, and then what are the different kind of materials that goes into this, right? There is a very a simple definition which we developed almost 10 years ago. It's called the renewable substitutability potential. The question here is, are there any system or materials that we could kind of replace with renewable systems? Remember the FR, which is the renewable portion of the purchase inputs. And then we do have another one, which is FN, which is a non-renewable portion. The question is, can we replace most of the FN with FR? Okay, the question is, how do we know this? Okay, there's an example here. For example, look at this. The University of British Columbia, the Center for Interactive Research on Sustainability, they've used flooring systems and so on and so forth. The question is, no, the simple thing here is it's easy to kind of replace, right? But how do you calculate? There are simple ways to calculate. This again comes from one of the publications we published almost a decade ago. So if you look here, basically what we're looking here is in terms of the potential of things, of the different materials which could be replaced with the renewable purchase inputs. And then what you see here on the left side, the graph is the entire lifetime of the building. If you recall A, B, and C, these are the different phases of the building, right? So kind of superimposed here. Again, going back to this slide, you do see this, that, this is exactly where we want to kind of make the change, wood. Okay, so I want to go back and talk about indices and then see how we can kind of make some changes. Again, FR is a purchase renewable input, and what we are supposed to do is to kind of make some changes in terms of the building materials. So this is a very simple example. In one of the examples, what we've done here is we ran some scenarios and try to kind of introduce materials or purchase inputs which have more renewable input in them, right? So basically what happens is we are pushing this line. This is again from 0 to 75 years, actually. This is in months, by the way. And what we've done is we have kind of looked at the total amount of solar joules, which is a yield, owing to all of the different things, including the maintenance. For example, the windows are being kind of replaced every 30 years. The roof is replaced by 20 years, and so on and so forth. So everything is kind of brought into this. The red line at the top, what you see here is nothing but the total amount of solar and joules. But if we are able to replace some of the FN with FR, which is actually the renewable purchase inputs, basically what we're trying to do is we're reducing the total amount of solar M joules that's being kind of stored in the building, right? So that's the whole idea. You won't be able to see this clearly, but you see here where there is materials manufacturing. I'm trying to bring the mouse here. Okay, and then you see here there are 3 different inputs. One is renewable substitutable, and then the last one is non-renewable. So what we're trying to do is we're trying to kind of bring a balance between non-renewable, renewable right here in order to kind of build a better alternative. Okay, so I'm just going to skip some of these things. Basically, this one talks about how we have literally looked at wood as an alternative, and then if you go back and see the solar M joules in terms of the intensity, the wood has very less intensity. It does have a lot of structural strengths which could be kind of used. We have done other work using wood as an alternative material for dome structures. You could actually Google my name and look for this in the Building and Environment Journal, right? Okay, so next question is, how do we kind of use an assessment? We want to kind of have an assessment tool that would kind of help us with all of these different things. One is looking at not just EMERGY, another one is also life cycle assessment, right? So we have developed this tool. This was developed almost 5-6 years ago. I still haven't made it public. So basically what this tool does is this tool kind of, takes all the different inputs in terms of materials that goes into a building. And then once, for example, you talk about flooring system, pretty much what we do is we have used the typical flooring system, and then we kind of break it down into different parts. What about the steel component that actually goes into the flooring system for, let's say, for fastening the floor to a system, right? We have kind of computed everything in detail. So basically, I'm going to the next slide. Basically, what I've done is, if you look at the item number 3, it's actually a building component way database. We can spend quite a bit of time to develop this. We do have an energy database which comes from Energy Star, and then we have RS means for the dollar amount. The reason is we want to have a one-stop shop tool, basically, to kind of run all of this analysis in one tool. I'm talking about EMERGY, lifecycle assessment, and so on and so forth, right? So we look at this. This is a simple example of how we develop the building component way database and so on and so forth. So this is a big picture in terms of inputs. Basically, we have an input, which is nothing but the building materials, the different types of materials. And then we kind of gather information in terms of transformators from the database. We have DALI constants, which is nothing but the disability assisted life in years lost owing to the emissions and so on and so forth. We use RS cost means to kind of gather information in terms of cost so that we can run the economic input output lifecycle assessments. We also run ecologically based lifecycle assessment, which is coming from Ohio State University, so that we can understand the different supporting services and so on and so forth, right? So the tool is here. What I'm going to do is I'm going to spend the next few minutes showing the tool so that you'll see how it's kind of being utilized and so on and so forth. And I'll be more than happy to kind of answer your question at the end of this session. Okay, so this is the tool right here. So what you see here is a tool. As I told you, we have the different materials which you can input. So all of these things are based on the construction specification institute system. We have concrete, we have masonry, we have metals, wood, plastics, thermal moisture, we have openings, specialties, and so on and so forth. As I told you, if you want to kind of understand or develop information related to EMERGY, we need to understand transformities. We do have transformed information right here. Some of these things would change depending on the EMERGY baseline, so which could be straight away, changed. Because we're also kind of using ecologically based life cycle assessment to also understand the life and years lost. We have some information here in terms of what is it, truck transport and whatnot, right? So these are something which we can input. So the idea here is, let's say if we make some changes, basically we wanted to increase the number of wood frames, materials in the building. So we just run this assessment and then we perform the assessment. And there you go. It's kind of a simple assessment. It runs a calculation. It shows information in terms of solar in joules. We do have information in terms of energy, which is terajoules. Emissions, this is going to be very critical. This is actually coming from the economic input output life cycle assessment developed by Ohio State University. So that's also kind of linked to this. And one of the interesting thing about EMERGY is, it kind of breaks down information in terms of the different ecosystem services. For example, provisioning services, regulating services, cultural and supporting services, right? So we have that information also right here. And here you can see the kind of impact of all of these different materials, right? I mean, concrete and wood and so on and so forth. So this is actually wood right now. It's kind of very, very less. Basically, our goal here is to kind of reduce the amount of concrete and improve the amount of in this example, the impact to human health, wood has the least impact. Concrete has the most impact right now. Okay, so in terms of emissions, again, wood is least, concrete is more, and so on and so forth. So this is again the disability assessment life in years lost. So that being said, I'll be more than happy to kind of talk to you about some of the work, what we have done. Feel free to kind of, check out our website, and then more than happy to kind of work with you guys. Thanks, Chris. Thanks, Sean. Back to you guys.
Thank you, Ravi. I think that's me now. Just a second. Okay. Do you all see a big video?
We see a current slide and next slide and some notes.
Okay. Okay, is that the title slide now?
Yes, sir.
All right, thank you very much. Thank you very much, Chris and Shauna, and thank you, Kiel and Ravi. So those were great presentations. Kiel challenged our assumptions of carbon neutrality with mass timber and asked us to radically expand our system boundary definitions and consider how to synchronize two complex adaptive systems, forests and whole building stocks, and to consider building as a terrestrial process. And Ravi's fantastic presentation, it was a critique of carbon and energetic accounting methodologies. And he took a closer look at EMERGY analysis as a conceptual framework and as a series of tools, and how we can use these indices and tools to properly account for the biophysical transformations that lie hidden behind construction processes, and to shine a light on the ecological infrastructure that these processes depend on. And what I understood is that he argued that if we use wood in the right way, we can move from a materials infrastructure powered by fuel to a renewable materials infrastructure powered by the sun. So what I'll argue today is that the technical organization of building assemblies themselves is ripe for radical integration using biomass. By biomass, I mean materials that naturally store atmospheric carbon because they grow by photosynthesis. And we need to design these biomaterials so that they can provide structure, but so that they also harness ambient energy for heating, cooling, and ventilation in order to achieve this integration. I'm going to show some examples of that my research group is developing now, and Kiel is heavily implicated in this work. Not only could these integrated biomaterials circumvent emissions from concrete, steel, plastics, and air conditioning, and so on a massive scale, I think they could also, the question is if they could also store atmospheric carbon for centuries, adding significant capacity to forest crop carbon sinks. So we all know that construction and building use accounts for almost 40% of global greenhouse gas emissions, and that a significant portion of these emissions come from producing concrete, steel, and so on. And that if we are going to avoid runaway climate change, we need to radically decarbonize the industry in the coming decades. And to do that, we need to find ways of negating emissions at the gigaton scale fast. One of the main hurdles, I think, is the overcomplicated technical organization of modern building assemblies. So here is a diagram of how modern building assemblies are organized. There are four main subsystems: superstructure, exterior envelope, interior systems, building services, each attending to their own functions. Each subsystem has its own repertoire of materials, components, and products to call upon in the service of these functions. This blueprint, which all modern buildings share, doesn't represent some high point in technical evolution. Instead, it reflects the organization of labor, knowledge, and risk in the construction industry. It's an organization that's pretty resilient, economically speaking, but which is fragmented and unsustainable, ecologically speaking. It forces the evolution of building technology to be siloed into these categories. As a result, we have a surfeit of over-specialized materials, a product market flooded with junk from a globalized supply chain, filling niches that need not exist. Instead, suppose we design biomaterials that give structure to the building and provide low-grading heating and cooling and ventilation, not by adding dissimilar materials and gadgets, but by shaping the biomass to coordinate ambient energy exchanges. Then we could radically simplify building assemblies and negate the emissions from cladding, insulation, ducts, air conditioning, and all the hidden materials you never think about. One-to-one material substitution is good, but not enough. What we need are monomaterial structures or close to monomaterial structures that can replace as many other materials, products, and components and systems as possible. To achieve this kind of radical integration, we need to design material architectures that orchestrate heat and mass flows at specific scales. To illustrate, I'm going to give you an example from nature, how termite mounds work thermally. But then I'm going to surprise you by arguing that we don't need to mimic natural forms to replicate the behaviors of interest. But to understand termite mounds, you first need to understand what buoyancy ventilation is, because it's one of the key mechanisms for recycling ambient heat. Harnessing thermally driven ventilation is not an exercise in the aerodynamic shaping of wind. As such, the form of the building doesn't matter much. What matters more is the topological organization of interior space in relation to heat sinks and heat sources. In this video, what you're seeing is a physical simulation of how buoyancy ventilation works. The simulations show two different kinds of buoyancy ventilation. One is displacement ventilation, which is good for flushing excess heat in the summer. The other is mixing ventilation, which is good for naturally recycling exhaust heat in the winter. So now that you have a moving mental image of how buoyancy ventilation works, we can visit a termite mound and understand how it harnesses ambient energy for air conditioning. There have been a number of hypotheses to explain how they work, from wind-powered pistons to metabolizing termites to solar-powered chimneys. But scientists always had trouble getting direct measurements, in part because termites will attack any probe that enters the mound. Then in 2015, one team of Harvard scientists overcame these difficulties, taking measurements inside a live mound for the first time. They studied the mounds of a particular species in India, which tend to be built in shade and away from wind. And they concluded, to the surprise of many scientists, that the thermal mass of the material, was the thing that regulated everything. So let me explain here. First, you have to understand that the mound is split into two. There's the top part, which is essentially the thing that is powering the air conditioning system, and the part at the bottom, which the air conditioning system is in service of. And that is the fungus farm. Termites invented agriculture long before Homo sapiens. And what the mounds need to do is to maintain tight levels of temperature and humidity for the fungus to grow, and then also to exhaust carbon dioxide from the air and replenish it with oxygen. Termites themselves are pretty thermally resilient, so it all can be explained from the fungus, these incredible mounds. So what happens, how the thermal mass powers the AC system is as follows. So at nighttime, the mass towards the exterior of the mound cools down, and this sets up a temperature gradient. So the mass towards the inside of the mound is relatively warmer. And so in the central air conduit, the warmer air rises, and then it falls when it falls on contact with the exterior cooler mass. And this sets up a ventilation conveyor belt, and that allows that transports the carbon dioxide from the fungus up to the chute. Up through the chute at the top, there are pores which, by diffusion, let through carbon dioxide particles and then let in, also by diffusion, oxygen particles. And this continues while maintaining the moisture inside the loop. During the day, the cycle flips. So the mass towards the exterior heats up, and the air cycle flips as a result. But importantly, it continues day and night. Right, so that is how the termite mounds harness exterior temperature oscillations to do thermodynamic work. As I mentioned before, your building doesn't need to look like a termite mound to work like one. You can couple buoyancy, ventilation, and thermal mass in a natural feedback cycle, up during the night, down during the day, just by getting the material proportions right. The key is using the right thermal scaling rules. And it turns out that these scaling rules apply to practically any construction material, even wood, which is not normally renowned for its thermal mass properties. In 2019, I defined these scaling rules mathematically. The ratios show you how to optimize an internal thermal mass so that for any chosen free running temperature, you can maximize the buoyancy ventilation it produces. The contour map represents the design space, and the blue spine shows designs where the thermal mass and ventilation exchanges are perfectly synchronized in a diurnal cycle. We packaged these scaling rules up in a free app and also in a Grasshopper definition that's also free to download. You choose the thermal mass material, the temperature damping, and the rate of buoyancy ventilation you want the thermal mass to produce. The app then returns the optimal thickness and surface area of the internal thermal mass. With these new scaling rules, we can play some interesting massing games. We'll use Jennifer Bonner's house gables as an example by asking, at what point do these CLT roofscapes start to doing the same thermodynamic work as a concrete thermal mass? Here's what the results look like for a small building. The size is defined not by the footprint per se, but how much ventilation the mass produces and how many people this rate of ventilation would serve. In this case, the mass produces enough ventilation for 10 people. And both buildings are sized to produce that same amount of ventilation and the same free running temperature. It turns out that wood can do the same thermodynamic work as concrete, but you need 80% more surface area in this case, which could be taken up by the gabled roof. Notice how the embodied carbon for the wood massing ranges from negative to positive. This defines the carbon storage opportunity, but also the risk. The final value will depend completely on where you source your wood from and how confident everyone is on whether that forest sequesters net carbon over time. And as Kiel explained, that is an incredibly complicated and risky business. Here's a medium building defined as an internal mass that produces enough ventilation for 50 people. The required surface has increased substantially for both massings, but the wood massing still needs 80% more surface than the concrete massing. This multiplication factor changes with the temperature damping you choose. More temperature damping, more surface. Finally, here are the results for a large building serving 100 people. Notice that the error associated with the surface area, for a wood massing, the error is as much as 400 square meters squared, or 16%. That's because I've used generic thermal property values for softwood with a large uncertainty range. You can use more specific thermal property values, but generic values are fine for early stage design, for early stage massing. Here a summary of the results showing how everything scales. What's important to emphasize here is that each of these pairs, concrete and wood, performs equivalently. The same free running temperature, the same rate of ventilation production. This is important for any life cycle analysis or EMERGY analysis or carbon accounting, because you can't do a fair comparison unless you have a well-defined functional unit. Kiel and I are working with a team of researchers at Rural Studio at Auburn University in Alabama and at McGill to test these scaling rules in real life. On the left are some pilot data for small pods, 1 meter high, confirming that the coupling works. You can see the swing of buoyancy ventilation produced by the wood thermal mass. It goes up during the night, down during the day, predictable like clockwork. On the right, you see plans for larger test buildings that we intend to build at Rural Studio this summer. We hope to show definitively that wood thermal mass can perform as well as concrete thermal mass, so long as you have the right amount of extra surface. So the second example I want to give is more radical and moving more closely potentially towards a monomaterial envelope. Those previous internal thermal mass require external insulation. I've been interested in quite some time in whether we could translate some advanced thermal design principles from aerospace engineering to design envelopes not as insulators but as heat exchangers. So we the way that modern buildings work, we're all familiar with. You wrap up your building and super insulate it, make sure that it's airtight. Then you use a heat exchanger and ductwork to preheat incoming fresh air with energy from the exhaust air. All right. I've also showed you with those water bath models how you could do something similar, but completely naturally with mixing ventilation, where warm air spontaneously exhausts from the top because of thermal buoyancy, and that draws in fresh colder air, and the two streams mix, so you recover some of the heat that would otherwise be lost to the environment. I've been interested in some time on how we could translate that heat exchange principles to the envelope. And it works. It would work something like this. So you have an airtight wall, say, and consider that you've got heat moving from inside to outside because it always travels from hot to cold. Consider if there was a pore and some fresh air entered through those pores because of wind pressure. You can imagine there's going to be some heat recovery effect. The air entering will be slightly preheated. Well, what if we could optimize the pore size and spacing to balance the two heat flows, right? So that the heat carrying capacity of the air coming in is exactly matched by the heat conducting out in the other direction, and so you have a handshake. right? To balance the convection inflow with the conduction outflow, on fitting the material to the flow, so to speak. So there's that Goldilocks scenario where if the holes are too big, there's not enough contact between the cold air and the warm material, so the heat recovery isn't so much. On the other hand, if the holes are too small, there's too much pressure difference and friction to overcome. You'll need a big fan to do that, and that's counter to what we're trying to do. But there's this point where it's just right, and what we managed to do is take some thermal scaling rules from aerospace engineering, which were used to optimize the pores in components such as gas turbine blades for thermal management, and translate them to building envelopes. And our most recent publication, which was published in January, this is also a collaboration with Rural Studio. We showed that actually wood and biomaterials generally are the prime candidates for this translation because they have the right range of thermal properties. It turns out if you want to apply these optimization scaling rules to something like metal or wood, you'd have to have lots of tiny holes all spaced together, and you would need prodigious amounts of ventilation to pull through prodigious amounts of ventilation to get the heat recovery required, just because metal and concrete are highly conductive. But wood, on the other hand, is low conductivity, so it's quite easy to balance the outflow with the inflow at reasonable ventilation rates. What we found actually is that, and demonstrated with experiments, is that we can achieve passive house U values and R values with monomaterial CLT panels optimized in this way, and that we can do that sucking fresh air through with natural buoyancy ventilation at a rate that's about 10 liters per second per square meter of panel, which is about the rate of ventilation you would need for one person in an office building, according to pre-COVID guidelines. So that brings me to the end of my slot. So just to recap, what I've argued is that the technical organization of modern building assemblies is ripe for radical integration. And we should try to do that using biomass that stores atmospheric carbon. I think one of the main design challenges is how to shape and upgrade this biomass so it can harness ambient energy. Then you could get the 2-for-1, the 3-for-1, the 4-for-1 functional multipliers. And with these functional multipliers, there is a chance of decarbonizing the industry at the gigaton scale with a dual action. On the one hand, circumventing embodied and operational emissions, and on the other hand, storing atmospheric carbon in buildings as extensions of forest carbon sinks. So I just to kick off the conversation with Chris, Ravi, and Kiel, I propose that a couple of key questions are one, how can we harvest wood in a way that increases the carbon drawdown from managed forests, right? Just a simple question. And two, how can we best use this valuable biomass to decarbonize construction at the gigaton scale? Thank you very much.
Thank you, Kiel, Saul, and Ravi for your presentations. They are, as always, very informative and push us to rethink some things. Since Saul threw that question out there, I would love it if Kiel and Ravi could maybe respond to that as we start this conversation before we bring in any audience questions.
Well, I think it's Sal pointed out how complicated or complex the question of harvesting wood for timber buildings actually is, if we want to think about the carbon drawdown that Sal mentioned. And I'm fascinated by it ecologically, technically, socially, culturally. It's super complex, and I think it's, for me, it's the question. So I don't have a simple answer for it, and complex questions should never have a simple answer. But I know it involves expanding our system boundary. I know it involves changing our sense of energy and ecological literacy in architecture. So I think there's some immediate practical things that we can do, like change our system boundary and start to use some tools like Ravi introduced, or some tools that are part of the kind of Natural Resources of Canada toolbox for thinking about carbon flows. But we still need to be pushing some bigger questions, because even these tools leave us with questions once you get into them, right? I think they're extraordinary. But the basis of both of what I think what we saw today was getting much more serious about the biogeophysical inputs that go into forests and then go into timber buildings and vice versa. And that's a pretty radical shift by itself. But if I have to give a single answer, that's what it would be.
So it was great presentation, Salman and Kiel. So well, interestingly, if you look at the overall lifetime of a building, right, and unfortunately, the operational energy use consumes most amount of energy, and that's exactly where, Salman, your contribution comes into play, where you're trying to reduce that kind of operational energy use, right? So that's an amazing contribution. Again, if we can find alternatives to the use of these operational energy use, I think that would be the best option, because even when we ran some simulations looking at the total amount of EMERGY or life cycle assessment, right? I mean, pretty much it's so difficult because almost 60 to 70% is operational energy use. Okay, so I like the way how you kind of use the biological example to kind of come up with some designs which is kind of organically kind of solves some of those problems. So that's true. I do agree with this. And it's as a researcher, right, it's kind of not easy to kind of convince the professionals, especially getting them to understand the kind of impact of all of these materials. I'm not talking about wood, I'm talking timber, I'm talking about the conventional materials and the kind of effect it has on the ecosystems. Okay, so that's kind of even still difficult. I've never written a proposal to NSF with EMERGY term, not even once, because I know it's going to be again rejected possibly, or they would come back to me and say that I have a typo in my text. Right, yeah. Let's listen to some of the other questions and maybe we can answer them.
Well, perfect. So from the audience, there's a question that says here, what is to glean from a decade of architectural education and practice forced to endure ad nauseum pontifications on sustainability, green building practices, embodied energy, and most recently, resilient design and carbon accountability? So potentially, these discussions have resulted in systematic confusion between terminology like intensive, extensive, energy, emergy, potentially even carbon in that respect, and then efficiency or efficacy.
I can take the first shot. I can kind of talk about this. So the problem with the building rating systems are kind of, it's much more like a tailored system, and then go back to 5 years before, look at lead rating system. They never had life cycle assessment as one of the components there. Okay, and suddenly because everybody's talking about it, they said, okay, let's bring in life cycle assessment. The larger problem here is in terms of how do you assign points based on what is that weight? Is it based on a common CO2 equivalent something? We don't know that either, right? So it's kind of based on the committee, right? So, but one thing we should also agree as researchers and practitioners is that there is something for us to fall back, at least for this point in time, but it has to be refined. Okay, or a period of time it's going to be refined for sure. When we talk about efficiency, right? So efficiency kind of comes into multiple different forms. Operational energy use has a different types of efficiency. You talk about chillers, kilowatt per ton, you reduce it, it's amazing. But when you talk about materials by itself, I think the example what Salman or Kiel talked about, right? I mean, we could develop those efficiencies. in terms of energy, in terms of EMERGY, yeah, we do have efficiencies in terms of how optimal we can actually bring about a material that would still kind of improve the overall sustainability index of the entire house or home or the building.
Solid.
Just to build on that a bit, of course, there's a lot to learn from the last couple decades of thought that have gone into the field that's sort of described in this question. My own view is that paradigm of thinking was mostly focused basically on fuel efficiency, not energy efficiency, and it remains very beholden to hydrocarbon capital as a result. And epistemologically, I just don't see that as the kind of right basis. I think some ecological epistemologies that, like Ravi described this afternoon, help us understand much more, help us better characterize exactly what building is as a terrestrial process, not just as a kind of the fuel performance or miles per gallon of a building. So I think there's just bigger questions and other questions to ask that are deeply scientific and aren't just, in my mind, kind of historical questions. So I think that's part of it. But all the terms that are put up there, intensive, extensive, efficacy, and efficiency, those all come out of just a different epistemology, a different definition of the system boundaries of buildings. I think they're all relevant questions. They're hard to kind of talk about equally and comparatively, but I think there's important there. A lot of, yeah.
Yeah, I agree. I think yeah, there is a lot to learn from all the discussions that have been had, and that's a lot of effort. I think what helps, what we're missing is a fresh perspective, and perhaps the key pivot is to move from analyses at the single building level to and have a go at looking at the regional level, starting with, for instance, a particular managed forests, and running scenarios over decades and centuries for what that forest could actually produce, and then what those harvested products could like how they could trickle through a regional supply chain. And then how could we design those buildings and to last for decades and centuries, and to have that larger perspective rather than the single building perspective, and not to say that that's how every building in the future needs to be designed. It's not that we have to be controlled only at the regional level, but we're missing that perspective to see what's possible, I think.
And timber is just the kind of perfect material to do that. It's much more trackable than all the other kind of what I would call neoliberal products. Buildings are assembled out of products. They're no longer built out of materials. Wood is just much more easier to track. You can understand the web of life that goes into it. Everybody understands that there's a tree, there's a forest, there's a wood building. It's much harder to do that with a rubber gasket and a glass curtain wall or something like that. So we can learn how to think about buildings as a terrestrial process through wood. That's one reason we spend so much time on it. But it's also the one material that we grow right now. So it just makes most sense to use the sun and the moon and other things to power our building industry rather than hydrocarbon capital. Yeah.
Building on that, there's a question that's coming in from the audience from Mark Donfrio. What does an ideal forest building pedagogy look like? So I think some of the stuff that's being talked about right now between the three of you points towards maybe an educational need that shifts us away from rooted or grounded or entrenched educational processes. So within that question, so what does an ideal pedagogy look like for a forest building? Who are the key players and partners? I would like to suggest that the key players and partners in that happen to be the people that spoke last session, and then you guys. So from our perspective, that's where we see it. That's why we started with it. That's why we're interested in this upfront discussion of what we might define upstream contributors. But I'll leave it to you guys to argue about and potentially give another take on it.
Well, go ahead, Sal.
Start, just quickly. I don't think there's a set design pedagogy, and there's not a clear picture for that yet because there's too many scientific questions unanswered at the moment. But one powerful form of pedagogy that architecture has is design studio research, and if you can set it up, the problematic in the right way and with the right balance of expertise and interest, transdisciplinary, then it can throw up some interesting questions and potential approaches, but it necessarily has to be experimental and a lot of intellectual generosity from a lot of different perspectives.
And you're right, Chris, it does definitely involve our colleagues and friends in forestry. It involves working with fluid dynamicists and thermodynamicists and ecologists. It also involves working with sociologists. We have to understand the unequal exchanges, the environmental load displacements, the form of underdevelopment that are involved with forestry. For instance, we know in Canada that Indigenous women are disproportionately impacted by forestry in a negative way, right? We have to address that at the same time that we're thinking about heat moving through a monomaterial wall, or we're thinking about an EMERGY analysis of a building. So I think the best part about it pedagogically, what our students need to learn is that these are all multi-criteria questions, and we have to learn how to address them simultaneously. We can't just kind of draw very narrow system boundaries around certain things and pretend like we're addressing these pretty wicked questions about changing climates and justice and that sort of thing. So I find great pleasure in working with these adjacent colleagues, and I think this our experience is that students get incredibly excited about it as well. I think there's a kind of maybe a tacit understanding that buildings are no longer just little objects that you compose, or they're not performative objects, but they're big territorial systems, and we need a lot of different perspectives and voices to develop that pedagogy. So Mark, please join us in that. So we'll continue to invite you to come to McGill and participate in some reviews and that sort of thing. So I look forward to that discussion.
So, Kiel and Salman, if I may, right? So I noticed that there is a lot of silos in the mode at which we kind of use tools and teaching, pedagogy, and so on and so forth. Right? Very simple example, right? I mean, Kiel, when you started to talk about your research, you literally started with the farthest. Okay, I mean the boundary, right? Look at the system boundary. You started at a very high-level system boundary, but you did kind of put a boundary, right? And when I started talk, I kind of reduced the boundary a little bit to the site level. And then when Salman talked, he literally got into the space right there. The larger question is, is it possible for us to kind of break this silos and kind of, provide students kind of such kind of, a seamless integration of all of these different boundaries? And again, if you look at the performance, it's multiple different types of performances. Salman talks about the efficiency, the occupant, thermal comfort, and so on and so forth. While you're talking about carbon, while I'm talking about everything to do with the efficiency of the ecological systems. So the question is, again, it's very difficult to kind of come up with one tool to kind of capture everything. It will happen, but it's not immediate. But as long as we're able to kind of provide some of these insights to our design students in studios, that by itself is a huge breakthrough, I would say, that we allow them to think beyond, like you said, Kiel, it's just performative. It's not true. It's much more than that.
So there's a question here in the Q&A that I'd like to read. It's going to take just a second, but I'm gonna pose it to you guys. It says, what is the near-term pathway for architects acting on their client's behalf to utilize an EMERGY audit, such as what Dr. Srinivasan just presented to us, or even in some ways what Solomon's tools are out there doing. I think what the question here is asking is, how do we bring this into actual being, right? So, typically, is it specifically to provide a design and to manage its construction within the business environment around them, consisting of long ingrained contractor conventions and slowly evolving local codes? Given the many tasks on their plates as service providers, how can the industry on the whole add such audits to the process? So, this is using maybe some of the BIM questions that we've argued about in the past in terms of its helpfulness or hurtfulness towards the design of our built environment.
I can take this question first, and then let Salman and Kiel talk about this. It's a very interesting question, very good question. The larger question which we all have to ask is, will the owners understand the biogeochemical interactions that goes into the different building materials and its interactions with humans? Okay, so it actually starts at that very high level. I mean, if you take systems such as, building thermal comfort or energy consumption, everybody understands that, right? I mean, it's codified literally. Actually, came in existence in 1973. Everything is codified. There's a standard. People follow certain things, and then they just get certified before they get the operation certificate before they can even occupy a building. But it's not necessary for them to run even a life cycle assessment. It's not necessary, right? So again, it depends on the objective of the design, I would say, and the owners and their inquisitiveness in terms of trying to see whether they can actually balance ecologically, not just operationally or operational energy use, basically, right? So that's going to be tough. I'll tell you what the second problem is. The second problem, what we face is actually the tool. Okay, I love the way how Salman and Kiel has developed those tools. We have developed tools specific to EMERGY, but remember, whenever we develop tools, we rely on data that's coming, which was developed by, in our case, it was developed by Odom in early 2000. Things have changed because we focus on using those tools using a baseline, right? So the question is, what are the uncertainties in those tools? Okay, could that be legally bound by contract? And all sorts of issues are also there. So we need a little bit more focus. We need more experts to work with us so that we can actually kind of refine the tools before we can actually make them public. We don't want too many people suing us, saying, well, you said it's going to be this and it's not that. Salman, Kiel.
Yeah, thanks. Thanks, Ravi. I think, tools are incredibly important, and robust accounting tools based on validated data sets and meaningful data sets that are regionally explicit is incredibly important. I want to make a distinction between all-encompassing detailed accounting tools or simulation tools, which would allow people and teams to analyze in great detail a given design and compare ad infinitum, versus conceptual, physically based shortcuts and scaling rules that allow us to see cohesive and meaningful patterns that we can design around, right? So, the thermal scaling rules that I show, it's a bunch of mathematical ratios which are robust, and it means that you don't have to, simulate a million arbitrary cases to find the right building design. It means you could take the shortcut in half an hour to get your proportions right, and quickly compare wood versus concrete, for instance, and that they're robust, and we're getting the data now, test data to show that they're robust. So I'd imagine, the danger is when we say we need to expand the system boundary, that we get flooded by the complexity of that. The key is that with research and investigation, we need to find cohesive patterns that show organizations at different scales that we can talk around and discuss, and that are meaningful, and not that eventually we just have to black box to clients and other decision makings.
Yeah. No, I think that's a really important point, Sal. That you know, the way I interpret my own interpretation of EMERGY analysis is that it is a form of scale analysis. That it's looking at a very complex system and finding which orders of magnitudes actually matter in those systems, which materials matter, which energy flows matter, and it helps us kind of reduce the complexity and helps us figure out what we need to work on. Simultaneously, it helps me in my own work understand what the actual material geography and web of life is that goes into a building. So regardless of any number that comes out of it, there's great use for me as an architect in understanding what that material geography is. And that more recently, I've come to understand how that also is a map. That material and energy map is also a map of all the political and social and economic relations of what we call building, and it helps me understand, you know, forms of unequal exchange and environmental load displacements, et cetera. So I think there's a lot of use for it outside of any kind of and maybe this is one of the errors that we've taken away from sustainability, is the myth that there's a kind of optimal scenario after you simulate something 100 times and you find it's kind of most, you know, best version or something like that. That's kind of the opposite of what we're saying here. So we don't need to wait for a client or a building code to mandate, you know, a larger system boundary or a different method of thinking through energy and material questions. I think that's entirely upon us to push that and just make it somewhat self-evident in our own work and not kind of external demand placed on us.
It does seem like the role you guys are playing in order to circumnavigate or shortcut the time it's going to take to put some of these models into place is your education of the youth that's entering the discipline of architecture schools in terms of a changing pedagogy, and as they leave and go out into the practice, so that this is ingrained in them, the understanding that they don't have to wait. These models are there already. This is where they think and work kind of in an entrenched fashion. So it goes back to, I think, an education of our youth moving through our architectural programs at this point, and how they might take this information with them already and get out into the field and start practicing. I like the idea that we don't wait around on this stuff, Kiel. I don't know that anybody's ever suggested you waited around on anything. So it's wonderful to hear you state it again. You just got to do it. You got to push it and make it happen out there. We have a time for maybe one or two more questions here. So Peter Osborne put in the chat, how do your suggestions change the form of practice that architects follow? So this is, again, I think maybe a good moment for you guys to push further on how we can influence practice that maybe extends outside of just how we educate our students, but how will our current forms of urbanization, dependent on high energy density fossil fuels, need to change in order to adjust to new forms dependent on diffuse solar radiation, forests, and other diffuse forms of energy, in your suggestion?
Well, one thing is Peter writes that question from Canada and Quebec, where it's slightly less fossil fuel intensive because the significant amount of hydro powered electricity that runs Quebec. So he's already in a slightly better place. But I think it's deeply connected to our responses about pedagogy. I mean, Sal and I and our colleagues are committed to producing citizen designers and citizen scientists who understand these terms and methods and can act on them. I think that's just a kind of a fundamental obligation of what we're doing. And I think those students graduate and they have fundamentally different practices it's not just going into a practice and finding clients and that sort of thing, but developing entirely new types of practices that are somewhere between ecology and thermodynamics and building design is that is the fundamental goal. And we're just starting to see some of those students come out now that I think are designing how they're going to design with all of this in their toolkit.
Saul or Ravi, would you like to add on to that, or do you feel comfortable with Kiel's response there?
I felt that was very elegant, and I have nothing to add to that.
Well, we are towards the end of this session. We're supposed to conclude around 4 o'clock here. I want to go back to one thing, Kiel, which I think for me was very exciting to see you bridge the gap between the last set of talks and this one with the forestry. You had brought up in some ways this kind of smaller system approach to even getting our wood from standing timber to materials that might look towards more of a local set of networks and systems. What was exciting to me to hear from Scott Phillips in a last set of presentations as the forester from South Carolina is that they have an enormity of smaller mills. They have a layered hierarchy of structures. So it gives great hope that we can continue to be more nimble with our industrial processes to drive down maybe from some larger scale infrastructures to have medium and even smaller scale moments that are pervasively laced across our region, particularly for Region 8. I could maybe bring in some of that discussion that you've already put out there of getting into our local architectures, if you will.
Absolutely. No, and I think that was a really important point in Christian Messier's presentation as well, is that we don't know what the forest is going to be necessarily in 30, 40 years, especially, I mean, it's just absolutely uncertain. So it's hard to predict what kind of infrastructure, you know, we build building material factories based on assumptions that we're just going to have a steady supply of spruce or white pine or something like that, but it's going to be changing considerably in this century. So we need to be thinking of building components, buildings, and even factories that can change and evolve with as species change, as climates change. We need cells, you know, envelopes that are heat exchangers and treating them as thermal mass to make them climate resilient, in the same way that we're making our forests resilient. So that's part of that, you know, the complexity of making forests as complex adaptive systems and thinking of buildings as complex adaptive systems. Like that's what we need to design. That's what we need to research.
So we're gonna end this session, but I want to say that this is a great transition because we're going to be moving into the industry critical systems, which deal with processing and manufacturing and logistics in the next talk. So hopefully some of those questions will be posed, and those people will be excited to answer them. I don't know, I don't know if the the industry is looking at scalar things, and so hopefully we'll find that out. We'll see what's going on with those groups. I want to take this one more moment to say thank you to Kiel, Solomon, and Ravi for your contributions to this symposium, but also to the larger wood agenda and for educating our youth. Greatly appreciate your time today and all of the work you're putting in front of us and behind the scenes.